There we go. All right, sorry for the delay, Alex. I had a little bit of trouble logging in again this morning. Logged me into one of those different meetings. I don't know exactly why that is. I think that, I don't know. But anyway, here we are. So, nuclear fission and chain reactions. So you see this reaction equation right here. Guess I need to get my pen out. So you see this reaction, and you see it's got this on both sides. That is a free neutron. So the free neutron hits the uranium-235, and that produces, that splits the uranium-235, making krypton-92, barium-141, and giving off 3 more free neutrons and a bunch of energy. Except this energy is not, well, if we're talking about a nuclear bomb, then this energy is what drives the bomb. But even though that's got volts in it, that's not the electricity that comes from a power plant. So chain reaction. Chain reaction starts with a free neutron, produces more free neutrons that then can go back to another uranium to make 3 more. So as you can tell, 1, 3, 9, 27, et cetera, and this could get out of hand in a big hurry, and that is exactly what happens in nuclear bombs. And we hope like crazy that we can avoid nuclear bombs. So let's see, in order to do what I want to do now, I have to change a window here. Well, this is being, some of my tabs are behind the, well, I had a tab set and I must have accidentally closed it. So that is, there it is. All right, so nuclear fission and chain reactions. Got a cute little picture here. I'm going to share a different screen. Okay, now with any luck, you should be seeing a picture in my browser. And so we've got what they're calling the incident, which means incoming neutron. And this hits the fissionable nucleus, which would be the uranium-235, and that splits it into these 2 nuclei, and it gives off 3 neutrons, which are incident for the next uranium. So each of those 3 neutrons can hit another uranium, and then each of them can split and give off 3. And this can continue to happen as long as there's uranium, fissionable uranium around. And that's when you get a chain reaction. Excuse me. So, you know, you can see 1, 3, each of those makes 3. So you can 9 in the next loop. Each of those makes 3. So 27 in the next loop. And we're talking about the subatomic scale here. They don't have to travel miles and miles to hit another uranium. They have to travel tiny, tiny, tiny fractions of a meter. So this can go very quickly. And if it's uncontrolled, kaboom, you have a thermonuclear explosion. Okay, we just frankly hope that we never ever have any more thermonuclear explosions in the world again. I mean, who knows, we may, but it's not our goal. But, whoops, just a minute, I can't just Alt-Tab, I have to change the share. So if we go back to the notes, that is what this is describing, right? Get out of the way, you stupid. Well, I don't think you can see it, but I've got a little control device at the top. And it usually hides, and it's not hiding, so I can't really reach the pen. Which is I don't know how to fix right now. Why won't it hide? Well, drag it to another spot. All right, so chain reaction then. In a nuclear power plant, we don't want the reaction to go full tilt. What good is it to make a nuclear power plant, turn it on, and instantly, boom, it's not there anymore. There's a big crater in the ground, and everybody for miles has been flattened, and everybody for hundreds of miles has radiation sickness. Not what we want. So we have a moderator. Moderator is a substance composed of lighter atoms that slow the neutrons, making them more likely to be absorbed, increasing the chain reaction. Well, okay, so we're not really talking about slowing it down here. We're talking about making it more efficient. Slowing it down will come here at the bottom with the control rods. So moderator, substance composed of lighter atoms, slow the neutrons, making them more likely to be absorbed by the uranium-235, increasing a chain reaction. Notice that hydrogen would be the ideal moderator, except that fast neutrons cause a nuclear reaction in hydrogen, so we can't just use plain nitrogen. And I'm not making this up. There is actually a substance called heavy water. Now, this right here is probably not expressed the best way it could be. Deuterium. Make sure you get this because people get it mixed up and they get things wrong. Deuterium is H with that 2 in front. Now that means that it is the isotope of hydrogen that has a nuclear mass of 2, 1 proton, 1 neutron. Most hydrogen is 1 proton, no neutrons. So deuterium is H2. Heavy water is water made from deuterium instead of regular hydrogen. So heavy water is H2, 2 hydrogens with a mass of 2, not the regular 1. Okay, we never write it, but regular water would be H2O with a 1 there, showing that it only had one atomic mass, a nuclear mass of 1, a proton, no neutrons. So this is deuterium. Heavy water is water that's made from deuterium. Regular water is made from regular hydrogen. All right. So the Canadians, for whatever reason, like to use deuterium. America and a lot of other countries, maybe because they can't get heavy water as easily, I don't know. I'm not 100% sure where heavy water comes from. I think it's naturally occurring, is my understanding. And it's my understanding, although where I heard this, I can't remember, so I can't vouch for its accuracy, that heavy water tends to be found at the very depths of the Great Lakes because it actually is heavier and settles to the bottom. I mean, frankly, it's quite a bit heavier. Regular water is 18 atomic mass units, and heavy water is 20 atomic mass units. So that makes it a little better than 10% heavier. So that's actually a pretty significant difference. We can use regular ordinary water as a moderator if the percentage of uranium-235 is increased, and that is called enrichment. Now, if you pay attention to the news at all, one of the big issues with Iran is that they keep trying to enrich uranium, and that's what we're talking about right there, increasing the uranium-235 in your sample. They do it with centrifuges, things that spin super fast and let the centripetal force separate the different elements. I think they have to gasify it, and then they spin it, and it separates into the different elements. And Iran keeps saying, well, we want to have nuclear reactors, and we want to use water as our moderator. And we keep saying, no, you don't really want nuclear reactors, you want nuclear bombs. And I guess I can have my opinion, but whether I really know what Iran is thinking or not about nuclear bombs versus nuclear power, I don't know. But I understand why we don't trust them, and frankly, I understand why they don't trust us. But that's the enrichment issue. Now, in nuclear power plants, we do not want the chain reaction to happen full tilt. We want it to be efficient, but we also want to be able to control it. So in nuclear power plants, control rods made of cadmium, heard of cadmium, the cadmium bunny comes out at Easter with chocolate eggs. No, that's Cadbury bunny, never mind. Cadmium's rods move in and out between the uranium rods to control the speed of the reaction. So basically, now this is oversimplified, you've got these uranium rods, which are much more smooth than I'm drawing. And then you've got control rods made of cadmium that can go in between them. And again, pretty pathetic looking drawing. So if we need the reaction to speed up, then those control rods move farther up to, however far up here they need to move to block the neutrons. And if the reaction needs to slow down, then these rods can be pulled out. And so they can move in and out as needed to control the speed of the reaction. The control rods, fuel rods, do tend to glow blue. That's called this Cernikov effect. And let's see, now I want to look at some pictures of how these things work. Let's see, new share. Wait a minute, I have to switch to that window, get the right tab open. All right, so here's a general idea of what a nuclear power plant looks like, how it works. Well, that's way too big. So here we've got, I got to get a finer point. That's too fat. So right here's the reactor vessel. In this vessel is the control rods and the fuel rods. This vessel is full of water. And as the fuel rods undergo fusion, they get very, very hot. And this water, this heats the water. Now it is pressurized, so it doesn't boil at its regular 212 temperature. It boils quite a bit higher, but I don't know the exact temperature. And basically, this is a pump, and this pump just keeps circulating water through. It heats up and it circulates through, and it heats up and it circulates through. So notice that the water that is actually in contact with the control rods is staying in this closed loop. Now, what we're seeing in blue here is more water. So this water is pumped into the steam generator, and this is a closed system also. But this steam is this water is allowed to boil and make steam pressure. So it makes steam, which is pressurized, and that steam pressure then is blown out through this turbine. We're not talking about an Arab's hat here. A lot of people would say turbine. And basically a turbine is a backwards fan. So you know how you put a fan in the window in the summer and you turn it on and you blow air through. And then one day we get a cold, windy day, and so you turn the fan off, but the wind blows through the fan and still makes the fan turn. Well, that's basically what a turbine is. I've never tried it. I guess someday I'll try it. That's an interesting idea. I've never tried it, but probably if you unplugged the fan and connected a voltmeter to the prongs of the plug, you would probably find that the fan that was being turned by the air blowing through it would start acting like a generator and producing a small amount of voltage at the plug. Not very much, because it really isn't turning anywhere near as fast as it would need to make a 120 volts. But anyway, a turbine is a backwards fan. By that I mean, instead of the fan turning to make airflow, gas flow, the gas flow turns the fan. It is basically the same thing, Conrad, as a turbocharger, except the turbocharger has another fan on the other end pumping air in, and this has a turbine has a generator connected to it making electricity. So this pressurized steam is forced through the turbine, which turns a generator and makes electricity. But then the steam is shunted to a condenser, where it is condensed back into, they're showing the droplets here, where it is condensed back into liquid water, and then it can be used again. So this is part of how we contain the radioactivity. The water in the reaction vessel is used and reused and reused and reused and reused and is not released back into the environment. The water in the steam generator is recycled and not released back into the environment. And then cold water from some outside source is pumped into the condenser and then back out, and used to cool the steam and condense it back into water so that the cycle can go around and around and around. Now, this does not look like your typical nuclear power plant to you, probably, because let's see now. Because, and I switched tabs, but I'm not sure if you're seeing the tab I'm seeing. I think you're seeing the tab I'm seeing. If not, you'll need to let me know. And how do you know if you're seeing it or not? I don't know. So right here is a big old silo thing, or a big old, like, enormous chimney looking thing. And that's what we're used to seeing with nuclear power plants. We still have everything else in this. The reason I started with the other picture is the other picture seemed a little simpler to understand. So here we've got the uranium fuel in the reaction chamber. And they're kind of giving you a little idea of the control rods, even though you can't see a distinction between control rods and fuel. And this is looping water. Let's see, which way does it go? This is looping water through the steam generators and putting this water back in so that it stays isolated from the environment. It makes steam in the steam generators. The steam generators cause the turbine to turn, which runs the generator, which makes electricity. And then this goes back to this condenser, and the water is able to flow back into or be pumped back into the steam generators. Now, in the case of this big silo system, this is using some cool water source, maybe a well, maybe, I think that the ones on the Great Lakes use water from the Great Lakes. I think there's one on Saginaw, on or near Saginaw Bay, that uses one from Saginaw Bay, water from Saginaw Bay, but I'm not 100% sure on that. And in this case, the cool water is pumped through the condenser. Warm water comes back in and is cooled down, and some of it is given off as that big cloud of steam you see coming as the cool water source is heated. Some of it is reused, so some of it is reused, but some of it is changed to steam, so we have to have more cool water being pumped in to replace the steam as we go. So ironically, nuclear power plants don't actually use the energy from the uranium fuel directly. They heat water, which heats water, which turns a turbine, which probably, so we've got what? Heats water, 1, which heats water, 2, which heats the turbine, turns the turbine, 3. So we've got 3 conversions in there, and every conversion, second law of thermodynamics, loses energy. So it's probably not the most efficient way to converted in the world, but it's a way that works. And you can't just harness the electricity straight from the chain reaction. Now, nuclear power plants have been, yay, a savior, boo, a terrible danger, yay, a savior, boo, a terrible danger. When we first started making power plants, they were like, wow, look at this amazing amount of energy with minimal pollution. And then, about the time I was in college, there was a 3 Mile Island incident on, I don't know, New York, someplace on the East Coast. What?
I don't know. It seems like Connecticut-ish.
My wife thinks it was Connecticut, somewhere on the East Coast. And one of the, I think they had 3 reactors, and one of the reactors stopped functioning and was in danger of melting down, but I don't think it ever did. And then there was Chernobyl, which was a huge disaster, and the Russians lied about it. They basically had a reactor meltdown, and you could actually, apparently from airplanes flying over, you could see the red hot from through the roof. The roof, I don't know, collapsed or something, blew off, I don't know. And so like everybody's, ooh, this is terrible, this is dangerous. But then with, take it or leave it, like it or not, agree or don't, I'm not making a statement about the truth, the veracity of it. But with all the concern about climate change, these nuclear power plants don't make greenhouse gases. So Europe particularly was all, yay, nuclear. Well, we've got it figured out so we can avoid the accidents. We're going to all go to nuclear. And then there was Fukushima plant in Japan that was 10 years or give or take ago, hit by a tidal wave. And then all of a sudden, oh, boo, maybe it's terrible. Maybe we shouldn't do that. Let's stop all the nuclear power plants we were going to build. So I don't know. They're up again, down again. First they're good and then they're bad. And we just can't quite seem to decide. I don't know the answer. I'm just telling you what's going on. So I don't know. Time will tell. Time will pass if the Lord doesn't come back, and we'll see what happens. Time will pass, and if the Lord doesn't come back, we will see what happens about nuclear power plants. And if he does come back, then it won't matter, I don't guess. All right, so let's see. Back to the notes. Now, I want to point out to you that these numbers are important. Uranium-235 and plutonium-239. One of the products of fission is plutonium-239, which is toxic. I mean, okay, so uranium is radioactive, don't know how toxic it is. Plutonium-239 is toxic, and it can be made into nuclear weapons. So when we start talking about nuclear reactions, it's not what we're always used to hearing about when we're talking about chemical reactions, where, you burn gasoline in your car and the gasoline's gone, and you've got carbon dioxide and water. Carbon dioxide and water are totally worthless for energy, regardless of what the crackpots on the internet who say you can run a car on water. Regardless of what they say, carbon dioxide and water are energy empty. But when we get to nuclear reactions, then things start to change because we can make this plutonium-239, and If you mix things right, if you add the plutonium and some uranium-235 and some uranium-238, then the plutonium will undergo fission also and can start to act as a fuel instead of a product. So we have this situation in nuclear reactors where if we do it right, our, smoke, to use the analogy of a coal power plant, actually then can become some of the fuel for a different kind of power plant. So it actually turns out that not only that, some of the uranium-238, remember 235 is the fissionable, most common fissionable form. Some of the uranium-238 will absorb neutrons and become plutonium-239. And in this kind of reactor right here, if we do it right, we can get 3 fissionable plutoniums for every 1 unfissionable plutonium used. So this is called a breeder reactor because it produces more fuel. It actually makes fuel in the process of burning the fuel, which is just weird given regular circumstances in power plants. All right, that's enough for the day. You have a quiz. Please make sure it's done by 3 o'clock. And then whenever you're done with whatever classes, I don't know what else, I don't know who else is doing what else, but whenever you're done with whatever classes you've got, you're at spring break, woo-ha. And we will see you online in, I guess it must end up being 10 days. Any questions? Well, all right then, you have a good day. We'll talk to you later.